Okay, in this video we are going to try and understand the 6 basic trigonometric ratios. Now it is very likely that you have learned them before, that you already know these 6 trigonometric ratios, but I promise you it is never a bad thing to get a review of the trig ratios. All right, so let's look at a right triangle here. Let's say that we have a right triangle and let's say that that this side over here is side y, and this is side x, and let's call the hypotenuse, we're going to call that side r, okay? And so here's the idea. We can, basically, given 3 sides, we can identify up to 6 ratios that are ratios of each of the sides. Let me show you what I mean instead of just saying it. We could create a fraction, okay, that is x divided by r, okay? So x over r. That's one possible fraction. Another fraction that we could do is y divided by r. So we could do y divided by r. We can also do x divided by y, so that's x over y. Okay. Now understand, we're trying to identify unique fractions where there are no duplicates. Okay. And so now what we can do is, well, look, there's no fractions where r is in the numerator. We only have r in the denominator, so let's do one where r is in the numerator. How about r over x? Okay. And we can also do r over y. So what we're seeing here is that it looks like each letter has 2 chances of being in the numerator. So we've already got r in the numerator twice, once over x, once over y. We've got x in the numerator over y and x over r. So now we're missing one. There should be another circumstance where y is in the numerator. And so we have y over r. So now let's do y over x. Okay? And here's what I'm telling you is that these are the only 6 possibilities of ratios between the 3 sides. Okay? And they're all unique. If I were to give a value to x and a value to y and a value to r, each of these numbers would be, well, unless any of these numbers were equal, each of these ratios would be a unique number. So let's, for example, say that x was 4, and let's say that y was 3, and let's say that r was 5. And you could use the Pythagorean theorem, and you can show that, that a squared, 9, plus b squared, 16 equals 25. That equals c squared. Okay. So what I would do here is I can have x over r. So that's 4 over 5. Whoops. Sorry about that. My little angled writing. 4 over 5. Then y over r would be 3 over 5. Then x over y would be 4 over 3. And then r over x would be 5 over 4. And then r over y would be 5 over 3. And then y over x would be 3 over 4. And so you'll notice that all 6 of these numbers are unique numbers. So they're different ratios depending on which of the 2 sides we're going to compare to each other. Okay? Now, this idea was formalized eventually, this idea of the relationships among the sides of a right triangle. And what probably somebody thought was this: well, you know, we could name the sides instead of just having letters. We could name the sides consistent names if we named them relative to one of the angles. So if we pick one of the angles, see, we got an angle here, there's one of the angles of the triangle, 3 angles. We got an angle here. We always have a 90-degree angle, and then we have an angle up here. And so these are the 2 acute angles of this right triangle. And the 90-degree angle doesn't change, so we're not going to name that one. We're not going to call them relative to the 90-degree angle. What we're going to do is we're just going to pick one of the 2 acute angles, and let's pick this one, and we're just going to call it angle theta. Okay, so there's the Greek letter theta. So that's angle theta. Now that we have picked one angle, we can now name this side and this side and this side relative to the angle theta. And here's what we decided to name them. I'm going to erase these letters. What we decided to name them, which you probably already know because you've probably already seen this before. Well, first of all, we know that the long side of a right triangle is called the hypotenuse. So we're going to put in here hypotenuse. Now we're going to use just HYP for short whenever we write out hypotenuse. Okay. Now, from angle theta, we now have this side over here that we want to name, and we have this side over here that we want to name. Well, what they decided to do is they name this side is right next to angle theta, right? And so right next to, there's a word that means next to, and that is adjacent. And so they decided to name this side the adjacent side. So adjacent. And then if we go across from angle theta all the way over here, the angle that's across from angle theta, it is on the opposite side of the triangle, so they call it the opposite side. So this side right here is going to be called opposite. And so relative to angle theta, this is the opposite side, this is the adjacent side, and this is the hypotenuse. Okay? Now, the names would change if we use this angle over here. So let's say up here we decide to name that angle. What if we called that angle angle beta? It's not really a beta. Let's make it a beta. It's going to be curved up there. There we go. Angle beta, another Greek letter. Well, if relative to this angle, this is still the hypotenuse. So we still have the hypotenuse. Okay? But now this side is next to angle beta. Therefore, this side magically becomes the adjacent side. And now this side over here is across from angle beta, and therefore this side over here magically becomes the opposite side. So each of the two acute angles has an opposite and adjacent and hypotenuse, but when you go from one angle to the other, the adjacent and opposite, they sort of switch positions because you switch positions on the angle, okay? So what we're going to do now is I'm going to get rid of angle beta temporarily. For now, we're just going to deal in angle theta, okay? So what we're going to do now is we're now going to create these same 6 fractions, these same 6 ratios, only instead of using x, y, and r, we're going to use the names opposite, adjacent, and hypotenuse. And so one possibility is that we can have adjacent over hypotenuse. So we can do this side divided by this side, just like we did x over r. We can do adjacent divided by hypotenuse. Okay. We can also do opposite divided by hypotenuse. So we can have opposite divided by hypotenuse. Okay. And then we can also do adjacent divided by hypotenuse or opposite. Okay, well actually let's do this. Let's make sure that just like both letters were in the numerator, let's do both sides, every pair of sides in the denominator. So we know we've already got 2 fractions that have hypotenuse in the denominator. We know we're going to have 2 fractions that have opposite in the denominator. And we know we're going to have 2 fractions that have adjacent in the denominator. Okay, there we go. Now, if we have opposite in the denominator, we have 2 of them. One of these is going to have to be hypotenuse, and the other one is going to have to be adjacent. Same thing over here with adjacent. One of them is going to have to be opposite, and the other one is going to have to be hypotenuse. And so here are our 6, the only 6 possibilities. Now understand that all of these fractions are relative to angle theta. Relative to theta. Okay? And so, relative to theta, we have adjacent over hypotenuse, we have opposite over hypotenuse, we have hypotenuse over opposite, that's this one over this one, We have adjacent over opposite, that's this one over this one. Then we have opposite over adjacent, that's this one over this one. And then we have hypotenuse over adjacent. That's 6 separate ratios, 6 separate fractions, okay? And so what they did was this, is they took these ideas, these 6 different possible fractions, and they named all of them relative to angle theta. And that's what we're going to do in just a minute, is I'm going to show you the technical names, the official names for all 6 of these ratios. All right, so let's name these 6 trigonometric ratios, okay? So the first one we're going to talk about is opposite over hypotenuse. And so we're going to put OPP over HYP. So opposite over hypotenuse, that is called the sine, S-I-N-E, the sine of theta, okay? It's called the sine of theta. Or another way of writing it is we use these 3-letter abbreviations, so S-I-N parentheses theta, okay? So sine of theta is the ratio opposite over hypotenuse, okay? All right, now let's do adjacent over hypotenuse. Well, adjacent over hypotenuse is called the cosine, C-O-S-I-N-E, the cosine of theta, or COS, cosine of theta, okay? And these are probably the 2 most popular ones, the 2 main ones, okay? Then the third one is called opposite over adjacent. So we're going to put opposite over adjacent. Okay, now the opposite over adjacent ratio is called the tangent. The T-A-N-G-E-N-T, the tangent of theta, okay, or T-A-N of theta, okay, tangent of theta. All right, and then, so now let's do a few other interesting ones. Let's now do adjacent over opposite. So we're going to flip this one over. We're going to put adjacent on top and opposite on the bottom. Adjacent over opposite is called the cotangent of theta, or COT theta, cotangent of theta, okay? And then we're going to do hypotenuse over adjacent is called the secant of the angle. It's called S-E-C-A-N-T, the secant of theta, or S-E-C of theta, okay? And then lastly is going to be hypotenuse over opposite. And hypotenuse over opposite is called the cosecant of theta. Cosecant of theta, or we write it as CSC, cosecant of theta. And so if you want, you're going to want to write these down. You're going to want a summary of these 6 ratios. And so that's what we're going to put right here. We're going to summarize the 6 ratios. And we're going to say that sin of theta, sine of theta, is equal to opposite over hypotenuse. And then the cosine of theta is adjacent over hypotenuse. And then the tangent of theta is opposite over adjacent. Then the cotangent of theta is adjacent over opposite. And then the secant of theta is hypotenuse over adjacent. And then the cosecant of theta is hypotenuse over opposite. okay? And now what we're going to do is I'm going to show you how, if you're given just one of these, if you're given just one of these 6 trigonometric ratios where you have a number over a number, you can find the other 5 simply by using a right triangle. So we're going to do that right now. All right, so let's say that we are given a right triangle, okay? We designate one of the angles as theta. Now the other angle is designated as beta, but we're going to do something with that a little bit later. And here's what we're told. We're told that the tangent of theta is 3/4. And we want to identify sine, cosine, cotangent, secant, and cosecant. Well, we can do this very easily simply by knowing our trig ratios and by knowing the Pythagorean theorem. Okay? So tangent, we know, is opposite over adjacent. So all we have to do is go find theta right here and enter 3 for the opposite side. So we're going to go to the opposite side over here and we're going to put a 3. And then we're going to go to the adjacent side and put a 4. So here's the adjacent side right here, not the hypotenuse, and we're going to put a 4. So now, with that, with knowing the adjacent side and the opposite side, knowing the 2 legs, we can now find the hypotenuse with the Pythagorean theorem. So if we do a squared plus b squared, not b squared, 4 squared. So 3 squared plus 4 squared equals c squared. 3 squared is 9 plus 4 squared is 16 equals c squared. 9 plus 16 is 25 equals c squared. Square root of both, and now c is equal to 5. So now we know that the hypotenuse is equal to 5. This is called a 3, 4, 5 right triangle. Very, very popular right triangle. Okay. All right. So now that we have the hypotenuse and we know the opposite and we know the adjacent, we can just identify all of the trig ratios. Well, the sine of theta is going to be opposite over hypotenuse. So that's opposite 3 over hypotenuse 5. So 3/5. The cosine of theta is going to be adjacent over hypotenuse. So adjacent is 4 over hypotenuse 5. So that's 4/5. The cotangent of the angle is going to be adjacent over opposite. So that's adjacent 4 over opposite 3, 4 over 3. 4 over 3. Now, you may be wondering, hey, what do these numbers mean? They are simply just proportional fractions of the side lengths. Given one proportional fraction of the side length, because all right triangles their side lengths are relative to their angle measures, what these ratios do is they connect you between the angle measure and the side measures. And tangent gives you a connection between the angle measure and the leg measures. Sine gives you a connection between the angle measure, one of the angle measures, and then the hypotenuse and one of the legs. And that's all these do, is they just create these trigonometric ratios. All they do is they create a connection between angle measures and side lengths, where the Pythagorean theorem creates a connection among all the side lengths, whereas these trig functions, they create a connection between angle measures and side lengths. Okay? So secant creates a connection between the angle measure and the lengths of the sides hypotenuse to adjacent. Okay? And hypotenuse is 5, adjacent is 4, so secant is going to be 5 over 4. Cosecant is the angle relationship between the hypotenuse and the opposite side. So hypotenuse 5, opposite side 3, so cosecant is 5 over 3. And so you can see how with the Pythagorean theorem, we were able to just take one of the ratios and then identify the other 5 ratios just using the Pythagorean theorem. Now what we're going to do is we're going to identify with this same information, we're now going to be able to identify all 6 trig functions for angle beta. Okay, so now this should be pretty simple, because all we have to do is look at our 3 sides and our ratios over here. But now what we have to do is, instead of 3 being the opposite side, since we're dealing in angle beta, 3 now becomes the adjacent side to beta, and 4 becomes the opposite side to beta. So now when we identify sine of beta and we want opposite over hypotenuse, instead of doing 3 over 5, we're going to do 4 over 5 because 4 is now the opposite side to angle beta. Okay, so sine is going to be opposite over hypotenuse, or 4/5. Now you're going to notice a pattern in here, and that pattern is accurate. Okay, if you think you see a pattern, it's probably something you can count on. Cosine of beta is adjacent over hypotenuse. So from beta, here's adjacent, 3 over hypotenuse is 5. So cosine of beta is 3 over 5. Tangent is opposite over adjacent, so that's 4 over 3. 4 over 3. Cotangent is adjacent over opposite, that's 3 over 4. 3 over 4. Secant is hypotenuse over adjacent. Hypotenuse is 5. Adjacent to beta is 3, so 5 over 3. And then cosecant to beta is hypotenuse over opposite. That's 5 over opposite from beta is 4, so 5 over 4. And so these are the 6 measures, 6 trigonometric functions for angle beta. Okay? Now, you may notice some patterns here, and I want to point them out to you. Okay? The first pattern I want to point out to you is note that tangent and cotangent are reciprocals of each other. That will be true every single time. Okay? Similarly, sine, notice that sine is a reciprocal. 3/5 is the reciprocal of cosecant 5/3. That is always true as well. Sine and cosecant are always reciprocals of each other. Similarly, cosine and secant are reciprocals of each other. Cosine is 4/5, secant is 5/4. The same exact thing happens down here for angle beta. Sine is 4/5, cosecant is 5/4. So sine and cosecant are always reciprocals of each other. Tangent and cotangent, always reciprocals of each other. And cosine and secant are always reciprocals of each other. The next thing that you may have noticed is that going from angle theta to angle beta, you may notice that sine of theta, 3/5, down here for beta suddenly became the cosine. Okay? And that is always going to be true. And here's the rule that I'm going to give you. Here's how it goes. Note that theta and beta, since this is a 90-degree angle and we have 180 degrees in a triangle, theta plus beta must equal 90 degrees. Okay? Because first of all, we know that 90 plus theta plus beta is going to be equal to 180, right? Because it's a triangle, right? Well, in order for 90 plus these two to equal 180, that must mean that theta plus beta must be equal to 90 degrees, right? I didn't put degrees on here, okay? Must be equal to 90 degrees. When this is true, when you have two angles that sum up to 90 degrees precisely, you will always find that the sine of one of those angles is equal to the cosine of the other angle, okay? And vice versa. You'll also find that the cotangent of the one angle is equal to the tangent of the other angle. And you'll also find that the secant of one angle is equal to the cosecant of the other angle. And that is a normal thing, okay? All right, so this is your introduction to the trigonometric ratios. And what I'm going to expect you to be able to do now is, just like we just did, if I give you any one of these 6 ratios, you should be able to put the 2 given sides onto a right triangle, find the third side with the Pythagorean theorem, and then be able to identify the other 5 trig ratios.